Welcome to a lesson with Dr. Powell. Let's suppose that we wanted to um, integrate the function cosine of x squared plus y squared, but we wanted to do it over the following region. Let's see where this is something like y is equal to square root of 1 minus x squared, and this is y equals 0. So between those in this space, in this semicircle, we wanted to integrate this. Well, this actually has a much nicer, this actually has a nice form if we think about polar coordinates. Let's see why. So let's think, we have cosine x squared plus y squared, and we're integrating over this region, dx dy. I'm not even going to think about the iterated version because what we're going to do, we'll think about that when we convert. But in the conversion to polar coordinates, recall that dx dy actually changes to r times dr d theta. And then we're left with cosine of, now wait a minute, x squared plus y squared, that's the same thing as r squared, because r conversion is just the square root of x squared plus y squared, the distance from the origin. So this looks like this is simply cosine of r squared right here. It's kind of nice. Okay, so cosine of r squared. So that's how it converts. And then let's think about what happens. Well, r itself looks like in the region is going from 0 up until 1, the radius. And then the angle is swooping around from 0 to pi. So hey, that's kind of nice. That's kind of like a rectangle in dr and d theta coordinates. So I mean, in fact, so for r is going from 0 to 1, and theta is going from 0 to pi. So to compute this integral, it's nice to think about polar coordinates now. In fact, you see a nice u substitution here. If u is r squared, then that's great because du is equal to 2r, and 2r dr if you want, because du over dr is equal to 2r. That's great. Or the derivative of u is just 2r. So we can divide by the derivative of u here to change this little thing to a du, which would give us du over 2 and a cosine of u. So basically you take this and you can replace dr with du over the derivative of u with respect to r, which is 2r, and that's where we get this canceling and this 1/2 popping out here. All right. So we just have cosine of u du, which is great. Now, of course, r was going from 0 to 1, and u is r squared, and r squared also goes from 0 to 1. So that's nice. Okay, so then we have d theta, and we have 0 to pi. Okay, now we take an antiderivative with respect to u, which we end up getting sine of u over 2, going from 0 to 1. Sine of u is just, well, it's actually sine of 1 all over 2, and sine of 0 is just 0. So that's kind of nice. So basically out of this, we just get a constant. And we're only getting a constant with respect to this variable here, d theta, as d theta goes from 0 to pi. So the antiderivative is just this times theta, then plugging those in. We'll end up just getting pi times that. So pi times the sine of 1 all over 2 would be equal to the this right here is equal to this integral that we started with, defined over this region, where we mapped out this region in the simpler coordinate system in polar coordinates. And in that conversion, we need to replace the dx dy by r dr d theta. Thanks for watching.